All right, let's take a look at the slides in chapter 16. Chapter 16 is about confidence intervals, titled Confidence Intervals, the Basics. All right. In chapter 16, we cover the reasoning of statistical estimation, margin of error and confidence level, confidence interval for a population mean, and how confidence intervals behave. So we have 4 objectives, 4 sections. Statistical inference about population. After we have selected a sample, we know the responses of the individuals in the sample. However, the reason for taking the sample is to infer from the data some conclusion about the wider population represented by the sample. Statistical inference. Statistical inference provides methods for drawing conclusions about a population from sample data. The population is our larger box, and the sample is a subset of the population. Collect data from a representative sample. Make an inference about the population. Simple conditions for inference about a mean. This chapter presents the basic reasoning of statistical inference. We start with a setting that is too simple to be realistic. Simple conditions for inference about a mean. We have an SRS from the population of interest. There is no non-response or other particular difficulty. There's no non-response or other particular difficulty. The population is large compared to the size of the sample. The variable, the second criteria, the second simple condition is that the variable we measure has an exactly normal distribution of n, well, we notate it with a capital N, mu, comma, sigma in the population. Remember, mu is the mean and sigma is the standard deviation. Oops, sorry. Oh. And the third criteria is we don't know the population mean, but we do know the population standard deviation. So for this section, we're saying something with our sample about the population where we don't know the mean for the population, we only know the mean for our sample, but we somehow know the standard deviation for the population. Note the conditions that we have a perfect SRS, that population is exactly normal, and that we know the population standard deviations are all unrealistic. The reasoning of statistical estimation. An NHANES report gives data for 654 women aged 20 to 29 years. The mean BMI of these 654 women was 26.8. On the basis of this sample, we want to estimate the mean BMI, labeled mu, in the population of all 20.6 million women in this age group. To match the simple conditions, we treat the NHANES sample as an SRS, a simple random sample, from a normal population with known standard deviation, sigma equals 7.5. To estimate the unknown population mean, BMI, mu, use the mean x bar equals 26.8 of the random sample. We don't expect x bar to be exactly equal to mu, so we want to say how accurate the estimate is. So we have a sample, we find the mean of that sample, but we don't expect the population mean to be exactly what we got from our sample. So we're going to give it a little cushion. We're going to give it a little plus or minus. The reasoning of statistical estimation continued. So number one was to estimate the unknown population mean mu, use X bar. And number two is the average BMI X bar of an SRS of 654 young women has standard deviation sigma divided by root n, which equals 7.5, the sigma they gave us, divided by root n. N is the number of young women, which equals 0.3 rounded. The 95 part of the 68, 95, 99.7 rule for normal distribution says that X bar is within 0.06 two standard deviations of its mean, mu, in 95% of all samples. So if we construct the interval of X bar plus X bar minus 0.06 and X bar plus 0.06 and estimate that mu lies in the interval, we will be correct 95% of the time. Adding and subtracting 0.06, adding and subtracting 0.6 from our sample mean of 26.8, we get the interval 26.2 to 27.4. For this, we say that we are 95% confident that the mean BMI mu of all women is some value in that interval, no lower than 26.2 and no higher than 27.4. Confidence interval. In our previous example, the 95% confidence interval was X bar plus or minus 0.06. Most confidence intervals we construct will have a form similar to this. Estimate, which is our X bar for us, plus or minus a margin of error. The margin of error, plus or minus 0.6, shows how accurate we believe our guess is. Margin sorry, got distracted by a notification. Okay, the margin of error, plus or minus 0.6, shows how accurate we believe our guess is. Margin based on the variety, the margin of error, plus or minus 6, shows how accurate we believe our guess is. Margin based on the variability of the estimate. Confidence interval. A level C confidence interval for a parameter has two parts. An interval calculated from the data, which has the form estimate plus or minus the margin of error, and a confidence level, which gives the probability that the interval will capture the true parameter value in repeated samples. That is, the confidence level is the success rate for the method. So 95% confident means 95% of the time, any sample we pull will be captured in that interval. Confidence level continued. The confidence level, the confidence level is the overall capture rate if the method is used many times. The sample mean will vary from sample to sample, but when we use the method estimate plus or minus margin of error to get an interval based on each sample, the percentage of these interval capture the unknown population mu. Interpreting a confidence level. The confidence level is the success rate of the method that produces the interval. We do not know whether the 95% confidence interval from a particular sample is one of the 95% that capture mu or one of the unlucky 5% that misses. To say that we are 95% confident that the unknown mu lies between 26.2 and 27.4 is shorthand for we got these numbers using a method that gives correct results 95% of the time. Confidence intervals for a population mean. In our NHANES example, wanting 95% confidence dictated going out 2 standard deviations in both directions from the mean. If we change our confidence level C, we will change the number of standard deviations. The text includes a table with the most common multiples. Confidence level C, which you can find these in table C, but here we have an excerpt. Confidence level C, 90%, 95%, 99%. The second row reads critical values Z star is 1.645 or 1.960 or 2.578. If you read down the columns, then what you're understanding is that for 90% confidence interval, the critical Z-score is 1.645. For a confidence level of 95%, the critical value Z-star is 1.960. And for a confidence interval of 99%, the critical value Z-star is 2.576. Once we have these, we may build any level C confidence interval we wish. Confidence interval for the mean of a normal population. Draw an SRS of size n from a normal population having unknown mean mu and known standard deviation sigma. A level C confidence interval for mu is x bar plus or minus Z star times sigma divided by the square root of n. Some examples of critical values Z star corresponding to the confidence level C are given above. That was the 90% confidence level has a Z star of 1.645. A confidence level of 95% has a Z star, a critical value of 1.960, and a confidence level of 99% has a critical value Z star 2.576. Oh, sorry, clicked out of the slide there. For slide 10 here, looks like my tablet's slow, frozen, something. All right, well, I have the book here, so let me take a look at the 4 steps for the confidence interval. Oh, that's loading. Try refresh. That's always a good one. Oh, I found where we are in the book. That's good. And our PowerPoints came back. So sure. Click yes. Click let us continue, please. View from the current slide, and we'll look at our 4-step plan. Confidence interval, the 4-step process. I find following steps to be very helpful. The steps in finding a confidence interval mirror the overall four-step process for organizing statistical problems. So remember, we had a four-step process for organizing our statistical problems, and this model follows that. Confidence intervals, the four-step process. Step one, state. What is the practical question that requires estimating a parameter? Step two, plan. Identify the parameter, choose a level of confidence, and select the type of confidence interval that fits your situation. Step three, solve. Carry out the work in two phases. Step one of step three, check the conditions for the interval that you plan to use, calculate the confidence interval, and then finally, step four is to conclude. Return to the practical questions to describe your results in this setting. So again, you want to state, plan, solve, and conclude. You want to ask yourself, what is the practical question that requires estimating a parameter? You want to identify the parameter, choose a level of confidence, and select a type of confidence interval that fits your situation. Often the problem tells you, find a 95% confidence interval. So for us, this is given to us. Solve. Carry out the work in two phases. Phase one, check the conditions for the interval that you plan to use. And step two, calculate the confidence interval. And three, return to the practical question to describe your results in the setting. How confidence intervals behave. The confidence interval for the mean of a normal population illustrates several important properties that are shared by all confidence intervals in common use. The user chooses the confidence level and the margin of error follows. We would like a high confidence and a small margin of error. High confidence suggests our method almost always gives correct answers, and a small margin of error suggests that we have pinned down the parameter precisely. How do we get a small margin of error? The margin of error for the Z confidence interval is Z star times sigma divided by root n, where Z star is the critical value based on your level of confidence. Sigma is the standard deviation of the population, and square root of n is the square root of the number of your sample size. The margin of error gets smaller when you erase it. The margin of error gets smaller when Z star gets smaller, the same as a lower confidence level. So the lower your confidence level, the smaller Z star is, because you're very closely tight around your mean in the middle. Or sigma is smaller. It's easy to pin down mu when sigma is smaller, but sigma is given to us, so we can't control that one. Or if n gets larger, so n is in the denominator, when everything else stays the same and the denominator grows, then the fraction itself shrinks, the value shrinks. Think of your measuring cups. A fourth is smaller than, well, let's start at the other end. A half is larger than a third, which is larger than a fourth, right? So the larger the number in the denominator of your measuring cups, the smaller the size of your measuring cup. So if n gets large, then since n is under the square root sign, we must take 4 times as many observations to cut the margin in half. So let's reread this one. How do we get a smaller margin of error? You have 3 choices. You make your confidence level smaller, or you make your n larger, because we do not have control over sigma.